like I said last time, we talked about memory, and there we dealt with kind of the defaults of CUDA memory types. We had our host memory, which we get through malloc, just like you would for a normal C program. We had global GPU memory, which you get with CUDA malloc. And then we had our basic memcopy, which can get things from host to device to host, or device to device. And of course, here's just little snippets to show what those different things are. This is basically what we covered last time. These are, like it says there, the defaults. There's actually other ways and other types of memory that you have access to through CUDA. Before we get to those, I want to give you a couple of properties of paged memory, which is the kind of default host memory. That way you can compare it to the types we'll get to next. So page memory, if you, I think all of you have either had or are going through computer architecture. And if you've kind of gone over the memory hierarchy, you know that memory is cached. So it goes from CPU tries to keep things that it needs in the level 1 cache, level 2 cache, the stuff that's close to the CPU and is fast to access. And then if it falls out of the cache, well, then it's in main memory. And if there's not enough room in main memory, it's not used often enough, then that page of memory is put into secondary storage. The same concept, it's that same concept. That's what we're calling page memory. So page memory can be moved around on the host side. And because of that, you may actually be waiting to retrieve memory from secondary storage, or it may be in the cache and it has to be moved to main memory for the GPU to use it. It can be essentially anywhere in host memory on any of the memory devices, and it's inefficient because of that. But because we allow it to be wherever it needs to be, we can allocate as much page memory as we want to, as long as we have the hard drive space. We could essentially max out RAM and whatever else and use secondary storage to store the rest. It would be inefficient, but you can use basically any amount of memory. So that's the kind of memory we've been using as far as the host is concerned. The alternative to that is pinned memory. Pinned memory, like it says up here, it's not paged. It's not going to go through the process of caching. It's not going to be moved from secondary storage to main memory and back again. It doesn't have that issue. It's instead always going to be at some area within main memory. CUDA can reserve a fairly sizable chunk of main memory, but that is all that you are allowed to use for this pinned memory. So it'll depend on the hardware, but generally this is around the hundreds of megabytes. So not a tiny amount, but not a huge amount either. It's usually plenty to work with for general purpose things, but maybe if you're trying to do something with large files or large amounts of simulation data, whatever it is, that might not be enough memory. But the advantage of it is you don't have to wait for paging. It's always in the same spot. You don't have to track it down, and that makes it faster to access. So you can see underneath here kind of a code sample that shows how to use it. The only real difference is that we have a slightly different function call in the allocation and deallocation step, where we would use malloc for the page version of host memory or normal memory allocation. Instead, we have to use CUDA malloc host, which is just like the CUDA malloc call, except it's putting memory on the host rather than the GPU. Then memcopy is exactly the same. You just treat it like host memory and use the same function call, the same arguments, all that stuff. And then to free it, instead of the normal call to free, we use CUDA to say CUDA free host, and we provide the memory there. So that is pinned memory. Any questions on paged or pinned memory? Okay, we'll continue. The next one is It would be wrong to call it host memory because it's actually kind of both. It's its own category called unified memory. So unified memory is available to both devices, and it's unique in that you don't have to make explicit copies to get data from the host to the device or vice versa. That all happens under the hood to you. When you're using managed memory, you just use like a variable and don't worry about where it came from or where it needs to go. And you assume that it is accessible because it will be accessible from either side. When you're using this, CUDA is going to move the data for you, so it's always available when it's needed. But because of that, it can be inefficient if you're moving data a lot. If you're not moving data a lot, then it can make your code more streamlined, and it can actually be somewhat more efficient in some cases where, again, you're not moving data a whole lot. Especially when the compiler can predict when you're going to need data and when you can kind of overlap the sending of some data with the computation of the data. That's where unified memory can really shine. But if you move data a whole lot, or you reference it from the host and then the device and host and device, and repeat that very quickly, it can be inefficient. So here we can see what this looks like in code. It's very similar to the other malloc calls. It's just CUDA malloc managed versus CUDA malloc host. If you were to launch a kernel, you can just use that same memory address, just like a device pointer. And then you can also immediately use it on the host side like I have for the sprint statement, without any need for a copy function or any sort of transfer. And then you just use CUDA free when you're done with it, just like a device pointer. And that's how to use unified memory. Any questions on this one? Okay. All right. So that's kind of all the general types of memory in the larger sense. We're going to get to kind of a more fine-grained memory storage possibilities here in a minute. But as far as like things that you would use on the programmer level, where you would say, okay, I want host memory, I want device memory, I want unified memory. Those are your options, and pin memory, of course. So now we've got those, we're going to move on to transfers. So we've got host device transfers, which is what you guys have already been using. There's unified memory, which we just talked about, where you don't have to copy explicitly. Device to device, which is just a CUDA mem copy between GPUs. If you have two GPUs on the same device, you can use that. You can also use it for the same GPU, but that's not really efficient at all. And then we had the last one, which is kernel memory transfers. This may sound complicated, but it's really not. Basically, if you take a kernel with two arrays on the device and you modify memory in that kernel, then that is a kernel memory transfer. So transfer data between locations in the same GPU. It doesn't work between GPUs. It's only in the same GPU. And it's a ton faster because that data is not going outside the GPU. It doesn't have to rely on a transfer bus, which is generally going to be slower than the GPU itself. So when you can, you want to use kernel memory transfers or do stuff in the kernel as much as possible and limit all of the others because there's a huge difference in bandwidth between them. Let's look at it in a moment. Real quickly, this is just an example that I threw together of kernel data transfer. Again, anytime you're changing data in a kernel, that's a memory transfer. But in this case, I chose to use this swap just to show that we're modifying arrays. It could be anything. Okay. So we kind of covered all the different ways we can transfer memory here. What should you use? So all of these are different box plots, and you'll notice when looking at these, they all have different y-axes, and that's because they're all very different values from one another as far as their range. So there's not really a way to put them on one axis, unfortunately. But the thing I'll point out, or the few things I'll point out, is the kernel copy. That's kernel data transfer. You can see it has bandwidth of around just 97, 98 gigabytes per second, which is extremely high, especially when you compare it to the rest of these. So the next highest being the device-to-device transfer. This is probably only fast because it's the same device. It can kind of short circuit and send it to itself faster than it could an actual other device. I didn't have another device to send it to, so that's where this number came from. And then next highest after that, and the highest out of the host memory transfers, is pinned memory. We would kind of expect that because it's in one place. It's a dedicated copy. So that's the next highest. And then you have page, and Unified actually finished this last year, but that's because this was a bandwidth benchmark. So all I was doing was sending data back and forth. If you do something in an application where this is used properly and you're not just constantly shuffling data, Unified memory can actually do much better. It's just that this was just a bandwidth test and nothing else, and it didn't perform well in that context. So, so yeah, that's everything I have as far as transferring data in and out of the GPU. Any questions on any part of that topic? Okay. So the last thing that I've got here is just a note about GPU memory. So in our first class, we talked a little bit about GPU architecture and how it has a memory hierarchy of its own, just like the CPU. And that's just what I've got again here. Of course, your register is the fastest that you can be, and then cache is a little slower, but still fast, and then global is the slowest type of memory that's on the GPU itself. And that still holds true. But the thing I wanted to add there is where the memory hierarchy kind of intersects the programming model for the GPU. So, so you have threads in the programming model. Threads execute a kernel. When you go to write a kernel and you write a local variable, like we've done for the index in some of our functions, that's a thread local variable. And because it's thread local, that means it's stored in a register, which is a good thing because that's the fastest type of memory to access. If you were to, well, there's actually something we haven't looked at yet. It's called shared. It's a, I can't think of the right word, but it's a keyword that you can add to a variable declaration. That means this is going to be shared by the entire block of executing threads. And that is what puts things in cache memory. Cache memory is still good, but it can only be shared by a single block of executing threads. So if you were to use 2 blocks and it relied on some shared memory, those 2 blocks are not going to talk to each other, and your algorithm may break because of that. So that's something to be aware of. And finally, global variables. So any parameter, well, I shouldn't say that. Any pointer or array parameter, any sort of persistent memory that you give to the GPU to the kernel as a parameter, that's going to be global, which is good because it means that any kernel of any size can access it, but it's also the slowest type of access. So the main point here is just keep the scope as small as you can when you're writing kernels, because that can affect the performance of each kernel that you write. And that's basically it as far as that. The other part of that is, like I said again, scope. If you declare something as being shared by a block and you have more than one block, you're going to have access issues. Same with thread local stuff. If you declare a thread local variable, then no other thread's going to be able to access it except for that one. It's going to have its own value. And that's pretty much it as far as GPU memory. That's all I have for today. So, are there any questions?